Welcome to Ask and Learn.
Here we are doing examples of finding the net force on a point charge with the force coming from a gravitational interaction with three masses on the vertices of a triangle, equilateral triangle. Uh, and just to set up, the force of gravity and magnitude is going to be the product between the two masses, and all the masses are the same. So m squared divided by the separation squared. But we'll have to also take into account force components which come from the vector nature of forces. So the first case that we're going to do is we're going to put the fourth mass right smack dab in the middle of the bottom part of the triangle, halfway between particle 1 and particle 2. And it always pays to draw force vectors to show what those look like, so that mass 4 is being attracted equally both sides, and it is also being attracted upwards. The two sideways forces are very noticeably balanced out. And so we really only have to worry about that y component up towards mass 3. So the net force on particle 4 is going to have 0 x component and just one calculation for the y component. And so we need the separation between that fourth mass and the third mass up above. And a little trigonometry can give that to us. So d over a is equal to sine of 60 or the square root of 3 over 2. And we can square that and put it into our relationships, and we will be ready to do this. Okay, so that is one example. Our next case, what we're going to be doing is placing mass 4 in the center of the triangle. So we want to drop perpendicular bisectors to each side. And those 3 bisectors meet in the centroid of that triangle. And so we again have a symmetric situation with the 2 side forces pulling downwards and positive x, negative x canceling, and the third force pulling up. And notice that those 3 forces appear to be canceling and setting themselves equal to 0. That has kind of the classical 3 vectors adding to 0. But it might be good to do just a short verification of that. I mean, clearly the 2 red forces have no net x component. But what about the y component? So let's take a look. They are all equidistant from the mass 4 is equidistant from all 3 masses. And so the sum of the y components is equal to f3y minus to, say, F1y. Okay, so F2y is the same as F1y due to symmetry. And let's see, so F3y is just equal to gm squared over d squared. And F1y is equal to g m squared over d squared times the sine of 30 degrees. And the sine of 30 degrees, of course, is 1/2. So we can see readily that multiplying it by 2 will give us a balance. And so even the sum of the y components winds up to be 0 in this case. So yes, the net force on that particle in the middle is identically 0.